So excited to have you here. Dr. Jane Wang is a senior research scientist at DeepMind, as you all know. Her background is in computational and cognitive neuroscience, complex systems, and physics. She's interested in applying neuroscience principles to inspire new algorithms for artificial intelligence and machine learning. I think that meta-learning is one of the big things for you that you're most excited about based on some of the things that I've heard and read that you've written. Jane received her PhD in applied physics from the University of Michigan in 2010. She's one of the UK's rising stars in cutting-edge artificial intelligence research, and she's one of the organizers of Women in Machine Learning, which a lot of you probably know her from. Jane's recent work focuses on reinforcement learning and meta-learning with fantastic successes, such as the recent release of Alchemy, as well as a variety of recent research papers in leading publications. In 2020, she wrote a post on her blog that I really loved. You should also check out her blog because she's got amazing short stories about futurism. And in this blog post, she imagines that the most powerful AI models of the future are going to be indistinguishable from magic. And so that's where we kind of want to kick it off today and start to talk. Jane, thanks so much for joining us here. Everybody, use your reaction buttons. Let's give a round of applause for Jane to join. Woo-hoo. All right.
Thank you all. I'm happy to be here.
I'm so excited to have you. We want to kind of kick it off by saying, it's Women's History Month, and we're really pleased to be having our first live interview with you. So I want to start off the conversation by first discussing who are some of your role models and why.
Yeah, I think that's a really important question, especially when you're in the Women's Appreciation Week, because growing up in science or just in general, you don't have a lot of women role models in science and technology. So kind of you're reading through your science book and it's just mostly men, and you don't see yourself in in their place as this person who will go on to do amazing scientific achievements. So I think for me, a lot of my role models were personal and people in my family. Like my mom, for instance, is a mechanical engineer. Well, I mean, she's retired now, but she sort of just by virtue of what she did, and it was just her job, and it has always been her job. It made me realize, just instinctually, that wasn't something that was off limits to me.
That's awesome. Anybody else, is their mom one of their role models? Give me a thumbs up in the chat if you are. That's exciting. So you started out with your mom's being a big role model for you. Are there any other women out there or others who have inspired you along your career path?
I mean, I feel like there have been so many female professors that have just been amazing at their jobs, and then honestly though, I might turn this around and say now I'm at the point where I'm actually really inspired by the young women that I see that are starting out, and they're just fearless, and they just have so much energy and passion and curiosity, and they're already kicking butt in the stuff that they're doing. So
yeah, I love that.
I think that inspires me to kind of keep going, almost just to know that they're out there. So
that's awesome. When did you first know that you wanted to be a scientist? Was it watching your mom as a mechanical engineer and being like, oh, that's awesome, I want to do that?
No, actually, so both my parents were engineers, and I actually thought that it was a really boring career at first. I originally wanted to be an astronomer because I really loved looking at the stars and learning about space, and I was really into science fiction. And so that's what first kind of drew me to science. But then, once I got into college and started to figure out what I wanted to do, I just thought, physics and science really was a big draw for me, because it seemed like it was so powerful to be able to understand how things work, and all the technology that can come out of just being able to understand something. For instance, the fact that these vaccines were developed in such a short amount of time and are deployed, and I mean, that's something
that is remarkable, right?
Yeah, it's just awe-inspiring. So I think I just wanted to really be a part of that and to understand how it was possible.
Well, so then you spent your graduate and your postgraduate work literally looking at human cognition, right? Like specifically, if I understand right, memory and memory-based decision making, and you use different imaging techniques like fMRI and others. You even developed some experimental approaches to neural processes in cell cultures, right? How important was starting out seeing how the brain works for your research? And was that kind of driven by this idea, like, I want to understand how it works, I want to be a part of this?
Yeah, definitely. And I think that's a great question because it's sort of, it gets at like the general framework of how you do science. For me, the first step of trying to figure out a problem or to analyze a data set is to always just get my eyes on the data, because our brains are incredibly good at spotting patterns, and like just be able to allow us to ask interesting questions. And of course, to be scientifically accurate, once you see those patterns and you formulate a hypothesis, you should go out and collect some more data. But sort of like the first formation of those hypotheses have to come from you just like kind of looking at the data and just being curious and exploring what's there. So I think like just seeing it like for myself.
That's great. You know, it's funny because that's kind of how I love to think about it, is that our brains collect data all the time, right? And like that's how we think about it at LDV, is that the vast majority of data that our brains collect and analyze is visual in nature, right? And so for AI to succeed, it's got to be able to analyze visual data as well. And so I love that, like, that's how your context behind this is too, is that like we are ourselves already, you know, analyzing data. And so that's what we're trying to replicate within these AI systems. And so, you know, kind of getting into how you started getting interested in looking at human cognition in order to develop a more effective framework for computer cognition. I've heard you say on other things that it's kind of two sides of a coin, right? That the neuroscience is trying to dissect the way that we think and how we analyze that data. And AI is trying to engineer systems in order to analyze that data. How did you get interested in looking at both sides of the coin?
I think it was just sort of like the natural progression of where I was, like where my research interests led me. It feels like if you follow, like the reason that I went into neuroscience is that I was just fascinated by the fact that you know, I have this brain and it seems to work in some kind of a logical way. And I was just always fascinated by how I problem solved. And but at some point, you know, you sort of get to this gap where it's like we don't understand where these thoughts come from, how they arise from the substrate of what they're made of, like these neurons and biological parts. And AI or like computer programs are sort of the other end, where you know, we can exactly specify how to do something logically, but we have no idea how to like bring it closer and closer to the way that, you know, like a human, like how thought forms. So I was just always really drawn to that like gap between those two parts. I was originally interested actually in brain-computer interfacing, because I was like kind of obsessed with this thought, this idea of being able to transfer thoughts from like brain to computer or brain to brain or something like that.
Fascinating, right?
Yeah. In order to do that, you have to understand how do you like program, what is the program of human thought? I like to think of it as like the human brain, the software of the mind as opposed to the hardware, which is like the brain and the substrates.
Yeah, that's exciting. I love that idea that it's the software of the mind. You know, it's funny that you talk about brain-computer interface. We had Thomas Reardon from Control Labs at our Vision Summit a couple of years ago. And it was, you know, just remarkable to watch what they could do with the hardware, you know, like a bracelet to interject the systems, the signals in order to do something like type. Right? It's absolutely crazy. And just thinking about, you know, kind of like the software and how we problem solve and things like that. You know, it's a great segue into talking more about meta-learning, which everybody's here to today. And I'm sure that we could talk, you know, Bayesian models and inference and all these kinds of things, and there'd be plenty of people in the audience who understands it. But it would probably make me go a little cross-eyed. So I'd love to talk about it a little bit more high level, and understand how we can be applying this. But as a foundation, you've talked about meta learning as learning to learn, right? You stated that was the best definition in your recent paper in behavioral sciences. Is that the definition that you think of, and that is the best way to describe it to everybody who's in the audience today?
Yeah, so I mean, for me, meta learning or learning to learn are the same thing essentially. And it's basically the idea that you can learn or improve upon a learning process itself. So to give an example, let's say you're learning a new programming language. The first time you do that, it's going to take you a lot longer than your second or your third programming language, because at that point you sort of understand like, oh, these things like case structures and for loops and like, strings and data structures. So so there's all this stuff that you learn the first time about the learning process itself, that the second time it's a lot faster now for you to pick up that second, third, fourth language.
Yeah.
And this is true for a lot of things that you're learning.
Yeah, it's super interesting. One of the examples that I'd heard you talk about is how, sometimes we learn how to understand what is most important for the task at hand, right? So like sometimes color is important if you're sorting things by color, or like you're putting together a puzzle piece, right? But sometimes it's shape, right? Like as I watch my kids try to put like different shapes into that cube to know like what's a triangle and what's a square, it doesn't actually matter what the color of it is. And so we learn how to do that automatically. And the second and third times that they do that, the fourth time, the fifth time, like the 25th time, they actually get better at it. And so you're trying to teach models how to do that as well. Do you think of it significantly different from deep learning?
I think that meta learning is orthogonal to deep learning. So you can do meta learning anytime there is a learning process with parameters that themselves can be learned. And it doesn't have to be via neural networks or deep learning. So for instance, I consider evolution to be a form of meta learning as well, because your genes specify your neurons that themselves learn. And so anytime you have sort of these like nested scales of learning, for some parameter you can adjust in your learning process, then you can have meta learning.
Gotcha. And so you talk a lot about the different scales of learning, right? And I'm assuming that like evolution is like the utmost scale of learning, right? That's intergenerational. Could you break it down for us a little bit? Like, how do you think about those different levels? What are the ones to really consider?
I would say that there's not like set levels or scales.
Sorry, I think somebody's volume is on. Can we just check our? There we go.
Sure. Yeah.
Gotcha.
Yeah, I would say that there's not. It's not that there are these set levels of learning necessarily. It's hold on a second. Let me switch to gallery view. It's that I think that learning is happening at multiple time scales all the time. So anytime you form a memory, you can do learning, and that memory can then impact the way that you're learning something in the future. So, because we're constantly always influencing our learning process as a result of things that we have learned in the past, I almost feel like it's not necessarily that there are these like binary or discrete scales of meta learning. Now, in my work, I've sort of have identified some more common ones. So like evolution, for instance, and then the way that your brain develops throughout childhood is like the way that, that your neuron synaptic connections are pruned. And then the way that the synapses themselves can strengthen or weaken as a result of experience. So those all happen at drastically different scales, and they all depend on those slower scales of learning as well. But that's not to say that there aren't other scales in there somewhere that are maybe happening at the same time or that are like in parallel.
Gotcha. And so I think that's the immense learning that I take away from that, is that we're all doing, like, our brains are doing amazing functions all at the same time that help us do everything from, like pick up our coffee cup through to understand the different trends, right, and make sense of the data, as you were talking about earlier. And one of the things that you know, like I've read about and that I've heard you talk about too is how bias starts to play a role in this, right? Like we learn certain things and we start to have certain bias, whether that's our preference of color, you know, or something along these lines. You know, is this a benefit to the way that humans think because it enables us to learn better, or do you think that this is a downfall?
I think it's both. So inductive bias pops up because it is beneficial when you can make assumptions about the kinds of problems that you're going to be presented with, or like the environment that you're going to have to make decisions in. Having an inductive bias essentially is just like an assumption that you can make that your environment is a certain way, and that helps you to learn and adapt much more quickly than if you didn't have those biases. So, I mean, this is kind of like a two-sided coin, similar with like stereotypes, for instance. So usually we consider stereotypes to be bad, but a lot of times they have some nugget of truth in them, and they can help us to make really fast snap decisions. Yeah. Whereas we wouldn't necessarily, like if we had to completely have taken all the information in an unbiased way and make a decision every single time, that would be really difficult for us, because we just have limited amount of time and information to make these decisions.
For sure. Actually, we've got a great question from Esther in the chat. Esther, do you want to unmute yourself and go ahead and ask?
Sure. One of the best and obviously most exciting / interesting examples of evolution / learning right now is the COVID variants, and how the fitness function that we represent is fostering the rapid growth. I'd love to hear you talk about that and just have some insights.
Yeah, that's actually a fascinating take. I hadn't thought about it in terms of meta learning before. Yeah, I think that with these, it just speaks to the power of being dynamically adaptive to an environment that also adapts to you. So it's interesting that, you know, the spread of the COVID variants depended on not only the like genetic variation of COVID itself, but also on people's actions, on the way that, you know, in certain communities, they are social distancing less often, and that's creating a positive sort of pressure for these fast spreading variants. And it's sort of, in a sense, learning to take advantage of our behaviors and the way that we're acting around each other, and then we are simultaneously adapting to COVID, and you know what our government is telling us. Yeah,
it's like we're learning, but the variants are simply evolving. I mean, we're adapting as individuals and changing our behavior, but the COVID variants, it's just like the worst ones are surviving and the rest are dying off. And so it's an interesting kind of divergence in the models, because one is learning and the other is kind of evolutionary selection of the behaviors.
I consider evolution, I mean, you can consider evolution to be a form of learning as well.
Yes, fair enough.
It depends on what
population learning.
Yeah. So what are you calling the unit that is doing the learning? Is it the whole population, or is it the individual?
Absolutely. And so, you know, I think it's, I guess the way that then I think about it, I should have given an intro to Esther, by the way. Esther is actually, she has been a cosmonaut before, so you might want to talk about astrology at a future date and time and space. But she's also an investor, and she's a CEO and founder of Wellville at the moment. She's been on our Women Leading Visual Tech series before, so if anybody wants to check out her interview, go to our website and check that out. But I think that the thing that I'd like to hone in on there, right, is like, what is our learning, right? Like, what have we learned about how the way that people respond to COVID and the way that it mutates, and how can we then apply that to our understanding of AI, right? Like, so how quickly people adapted their behaviors or didn't adapt their behaviors, right? Is there a learning out of this that we could take and apply to the way in which we can help to engineer systems or computer cognition that we hadn't before?
Not quite sure. I mean, I guess so. Trying to frame this whole like pandemic and our response to it in meta learning terms, I guess I would think that the meta learning we're doing is how we as a population can respond to such pandemics. And so I think we've taken a lot of teachings from what happened in 1918, the Spanish flu. And you know what, we look to the past, we look to history to see what did work or what didn't work, and we've adapted our strategies because of that. We, you know, we knew, for instance, that with the Spanish flu, it caused cytokine storms, and so we had to really be wary of our body's responses to COVID. And so we, I mean, I'm not like a epidemiologist or anything, but armchair looking at the stuff. But yeah, I feel like that we took so many lessons from that, and as part of the reason we had such a great rollout of the vaccine and like the super fast developments. I think nobody expected it to be this fast.
Yeah. And so, you know, like talking about how those learnings have impacted the way that vaccine rollout has gone and things like that, you know, which industries or sectors do you feel like they have the most opportunity to leverage meta learning now and in the future?
Honestly, I think all of them. I mean, anytime you have a learning process that can itself be tweaks or bettered, you can take lessons from meta learning. And I would just say that though, meta learning is not like a magic bullet. So it's just sort of this idea that the problems that you want to apply your algorithms to always have some structure, and you can take advantage of that structure by learning that structure.
Gotcha. So I'm gonna push you on that just a little bit. Can you give me an example of a problem, right, that you think is primed for a meta learning solution?
I mean, I wouldn't necessarily say prime. I mean, I would say that in most of the AI technology companies today are probably looking at problems that could use some aspect of meta learning, like self-driving cars, for instance. The fact that, you know, I think that maybe a lot of I'm not a self-driving car expert or anything, but it feels like a lot of previous companies have handcrafted these like visual recognition systems or object segmentation systems, and are trying to like create these hand-coded rules. But you could do something like where you have a self-supervised system that's sort of teaching and bootstrapping itself to learn to better recognize things in the future as you give it more and more data. I think like Tesla is doing something like this. So you can always like leverage more data.
So really where there's lots of data being collected, anywhere where there's tons of data being collected could be an opportunity for meta learning to be applied to, as another layer on top of what people are already doing in order to enable those systems to learn to learn. And actually Carol in the chat has popped in, you know, can you think of a specific example where meta learning could be incorporated into healthcare or treatment or management of patients?
That's a great question. Yeah, I think that I mean, like, so DeepMind has had some history in this as well. We're trying to apply, you know, machine learning to healthcare. I think that the tricky thing about healthcare is that you want to be quite careful. So the data, you can't just collect, the data is not free. You don't want to be accidentally giving somebody the wrong medication and risking somebody's safety for that. So you would need to think about ways of collecting data, like either in simulation or being able to leverage sparse data in a semi-supervised way, so that you're not, yeah, I mean, I think the thing with healthcare is that you really cannot afford to make a lot of mistakes. And with meta learning, it can be, I mean, it takes longer to learn a learning process itself than to just learn a problem. So it can be like computationally expensive.
Yeah. It's interesting because when we think about like all the different opportunities for meta learning to be applied, right? Like these are kind of also the opportunities where startups can interject themselves in order to bring about, a new solution that the legacy industry has yet to be able to deploy, right? Especially in like the meta learning side of things. And so it seems like, there's a couple of different questions coming into the chat right now about them. And I'd kind of like to apply them specifically into the startup space because we've got a bunch of different people who are representing startups here. So one of the first ones is from Lilith at SmartGate VC, and she wants to hear about using meta learning to BCI. What critical issues can it help to solve? And do you think that hardware is more limiting, or do you think we actually need better software?
Wow, these are all such great questions I hadn't really thought about in terms of meta learning before. So with BCI, so brain-computer interfacing, I assume is what they mean. I guess the critical, so you mean how can meta learning progress or advance BCI? I guess the primary problem in BCI is essentially like you need to train individually for each person almost, because you need to be able to translate between brain activity and whatever representation that you're trying to get out of it. Like if somebody is trying to move a cursor or something with their mind, then you need to sort of have a lot of training iterations with this person in order to be able to properly label these different representations. And they usually tend to be individual. But I guess if there was a way of capturing like structure across people, maybe you could say that, like, if you tend to have this kind of representation for moving a cursor, then you will also have this kind of representation for moving a coffee cup or something like that, or like to do some other kind of a movement.
Yeah. So it seems like for companies in the BCI space or startups that are starting there, this might be a really interesting way for them to start to develop their algorithms, is to think about it from a meta learning approach in order to become more efficient at scale, it sounds like.
Yeah, so you can imagine some kind of system which is figuring out, like, for each individual person, how do I optimize the way that I can collect the training data such that I can minimize the amount of time it takes somebody that needs to sit there and provide a lot of examples.
Yeah. I mean, I guess that stands kind of across the board, right? Like that's maybe like the biggest opportunity there is to be able to do things with a smaller amount of data than we currently need at the moment. And there's a couple of questions that are coming in regarding that I'd love discussion groups to kind of take on. And I just wanted to chat about a few other things before we break out into our groups. And one of them is timeline, right? Like how far are we in your mind from seeing AI truly learn to learn and transform aspects of our world in desirable ways?
Well, I mean, I think those are two separate questions. We already have algorithms that can learn to learn and can meta learn. There are limitations with learning to learn, though, and meta learning, in that you generally don't get great what we call auto distribution generalization. So if you try to train your system on something that it's just never seen before, it's hard for it to do something smart in that case, or to be able to generalize and to do transfer learning. So I think that's kind of a factor in that a lot of the AI algorithms that we have essentially can't do creative problem solving. Yeah. So they can't, come up with some insights to deal with a new problem that it's never seen before. Yeah. That to us makes sense. I think generally what we would expect if you present an algorithm with completely new data is that it would do something nonsensical, or or it would break or something. So
definitely. And so, that's kind of one of the things that you'd taken on in that blog post, right? And this idea of it being conceivably indistinguishable from magic is that creative element, right? So where you could like hum a few notes and it can generate a whole song for you, or you can give it a couple of bullet points and it can write out the content piece that you want to put out there. Do you think that this is in our future? How close?
I think it could be. I have no idea because it almost feels like that there is some kind of step function in our future that like there is some bit of insight that hasn't been taken yet, or that we haven't taken certain steps. Because the kinds of programs that we have now, AI algorithms, just don't have that ability to essentially replace a human. So a human is still going to be the best at being able to generate creative, interesting stories, and to be able to make an amazing song. We have amazing generative models right now, but they kind of just sound like they're remixes of all their training data.
Definitely.
If you look at like those deepfakes, they're all just like perfectly fine people, but they just look like a mixture of like just a bunch of people that you've seen. So I'd be anytime that we actually see an algorithm that can truly do some like creative design that makes sense, and that isn't just like a mishmash, a mashup of what it's seen before, then I will say that maybe this magic is close.
That's great. So we will also let those be discussion points for you guys to determine, listening to the conversation, how far do you think it's going to be? But before we hit discussion groups, just want to touch on two quick things. So one, has there been a moment in your career so far that you would consider your most defining event?
Actually, no. Like I feel like there wasn't a single defining event, but there was a defining period of my life in the beginning of my like towards the beginning of my postdoc, where I didn't really know what I wanted to do with my future, with my career. I had just gotten a PhD in applied physics and computational neuroscience, but I was sort of a little bit lost. And then I think that there's just something in the zeitgeist, but this was around the time that AlexNet made their breakthrough in the ImageNet competition in 2012. And I wasn't like consciously aware of this, but around this time I became obsessed with the artificial intelligence. Maybe it was the science fiction books I was reading or something, but I just got into my head that I really wanted to work on this, to figure out how to program the brain. And then everything just became a lot clearer after that. I was like, okay, I need to get a much better background in neuroscience, and then I need to get a much better like technical background, and it just, yeah, and I somehow like found myself at DeepMind after that. So
yeah, and so finding yourself at DeepMind, right? Like, given your interests and your studies and everything else, it seems like, you know, solving intelligence and then having intelligence that can solve everything else was a really natural next step for you. But we're, you know, just for people in the audience who are interested in like taking a similar route or really interested in DeepMind, were you recruited by them or did you just apply? And do you have a recommendation for them on how to catch the interest of the DeepMind team or perform well in interviews?
I would say that the path that I took is not necessarily applicable now, because I actually applied for the company when they were very early. So it was like in 2014, I think. They had a very sparse website. They hadn't had their Nature paper come out yet, the first one. And so I actually just like sent them an email, I think, with like a cover letter. And it was, so I wound up not hearing back for like, I think 3 months, and it actually went to my spam. So, so I like almost missed the recruiting email inviting me for an interview. So that is one piece of advice I would give you, is to like always check your spam.
Always check your spam.
And then, but then I think in general, I would say it's, you know, I guess going back to the thing I was talking about earlier, of just knowing like what is it that you're really passionate about. What is it that, like, what question really drives you? And then figure out how to get there. Like, don't worry about like departments or what paper, like the your education in the past, or like things that you think are going to hold you back. Just try to figure out like, well, what are the pieces that I need? What kind of knowledge do I need to acquire in order to be able to tackle this problem? And then you just position yourself in a place to be able to tackle that. And then I think people will see that you're ready.
Wonderful. And so, you know, figure out what that vision is and then the steps in order to achieve it. Love that.